Hello everyone, welcome back to a new video. In this video, we are going to discuss an AI of a classic game called Pocket Tanks. Now let's have a look at the demonstration of how the final project is going to look like. So let's have a look. Now there are two players that play this game one at a time. One is us, the player, and the other one is the AI that you can see in the red. These two players are actually tanks that can fire a missile to each other. The aim of the game is to try and hit the other tank from this missile. We can select what the angle of the missile launch is going to be and what is going to be the initial velocity, or we can say the initial magnitude of the speed. By making some certain adjustments, we can click on the screen and throw the missile. Now here it goes. Now, as you can see, I made the throw. The projectile went ahead of the enemy tank and it actually missed the target. But for the opponent or AI's case, it threw the projectile or the missile and it actually hit my tank. Therefore, the enemy gained a 0.1. We can try once again. Once again, you can see that I missed the target and the AI tank actually hit the target. That's why it gained a score of 2. Now, this is the advanced version of the game. The layout and everything looks exactly the same, but there is a difference in the motion of the projectile, as we can see. Let's shoot a projectile and see how the difference is. Now, as you can see, the motion of the projectile is not a complete parabola, but an variation of a parabola. As you can see, the AI of the enemy tank missed the shot and it did not hit us. Let's play a few iterations of this game and see how the AI tank will finally learn where to hit the target. Now let's do this. Now, after playing a few iterations, you would have seen that the AI of the enemy tank actually learned how to hit the target in a few iterations. Now we are going to discuss how the AI of this enemy tank did this. So let's do this now. Okay, so in the video, the cannon that you saw that went through the air and hit the other character or tank, as to say, was following something called a projectile motion. Now, projectile motion is the motion of an object in any form of 3D space. For our simple version of the game, we were using a 2D version of the projectile motion, but there do exist in 3D games a 3D version of the projectile motion. For our ease of study of projectile motion, we can divide it into two categories. One is the simple projectile motion, the one that you see on the right, and one is the advanced projectile motion that you see on the left. So let's first discuss what the simple projectile motion is. In a simple projectile motion, we can assume that the only force or to say acceleration that is acting on an object that is thrown from this start point to this goal point is only the gravity. The gravity will act only towards the down direction and it will try to decrease the speed, the vertical component of the speed of the particle that is going through the air. And that's why when a particle is thrown through the air, it will eventually come down and fall to the ground. There is no per to say acceleration that is acting towards the horizontal direction. So there is no reduction of speed over there and we are following a constant speed model in this one. Applying some basic mathematics, we can get the value of the angle theta is equal to the sine inverse of r times g divided by u square. Now u square is taken as the initial speed, only the speed, the magnitude of the complete speed. R is taken as the range that is from the start to the goal, and G is obviously the acceleration due to gravity. For the ease of implementation, we have taken U, the magnitude or the speed, to be a constant value that we can adjust according to our simulation. Well, according to any parameter of simulation, or we can say the speed of the simulation. Something like that. After we make the calculation for theta, we can finally get the horizontal component of the velocity and the vertical component of the velocity, which is simply the magnitude of u multiplied by cosine of theta and magnitude of u multiplied by sine of theta. Once we solve for both of these horizontal and vertical initial speeds, we can finally use these to instruct the character or the tank to say in the game to throw at this particular speed. So it will initialize the projectile with this speed and throw the object. Using this simple mathematical model, we can simply compute the starting velocities, the horizontal and vertical velocities. Now, how this is useful in our game? In our game, the opponent, that is the AI, already knows the distance, or we can easily compute the distance that is between it and the character, our player, that we are playing. So we already have this value of r, we already know g, and we have already set a value of u. Therefore, we can simply get ux and uy, which the AI can use to throw obstacles at us. As you can see, it is called a simple model, but it is actually a hard version of the game where the opponent has a very good idea of, okay, so this is all for the simple projectile motion. So in the advanced projectile motion, in the simple one we were assuming that there were no horizontal acceleration, but in this we are also considering a horizontal acceleration, which we call the drag. Drag is directly proportional to the horizontal velocity component at any point of the trajectory. So it will be given by minus k times vx. K is a constant that is set appropriately based on the simulation. Now, deriving a complete mathematical model like we did in the simple case, deriving the value of theta, is actually much more complicated in the case when we have a drag. It will result in exponential values and so on. For these complicated cases where we have an acceleration, a function of multitude of different values, we can actually make use of computational techniques. One such computational technique that we are using for the advanced AI is the binary search algorithm. In order to understand a binary search using an example, we can assume that I have thought of a number and you are to guess that number. Now we know the range to be 0 to 100. You can make a simple guess, let's say 50, and I will let you know whether the number that you spoke, the number 50, is it less than or equal to the number that I told you. Let's assume that the number that I took was 60. Now 60 is greater than 50, so I can say that the number that you guessed, 50, is actually less than 60. Now you know that the number that I am thinking of is actually not between 0 to 100, but it's now actually between 50 till 100. This way we are reducing the search space that we had 0 till 100, it has completely halved down from 50 to 100. Now the search space is now reduced to 50 till 100. Now what you're going to do is take an average of 50 and 100, a middle value that is 75, and you're going to give the value 75 to me, and I'm going to say that 75 is greater than the number that I'm thinking of. Now we have again reduced the search space from 50 till 100 to 50 till 75. This way, by taking the middle value at each iteration of the algorithm per to say, we can converge to the value that we actually want, the optimal value. Now we can apply the same technique, almost the same technique, to the prediction of the advanced projectile as well. Let's see how we're going to do this. So first of all, we choose two angles, alpha and beta, and throw the projectile what the trajectory is going to look like. So at alpha, if the projectile drops somewhere before the target, we will record it. And for beta, the projectile drops after the target. Now this is important that we need to take the alpha and beta values in such a way that one lies before the target and one lies after the target. Then for the next iteration of the algorithm, we are going to take theta, that is going to be the average of the two values, the value that is between alpha and beta. Then we are going to throw the projectile again. Now we are going to have two scenarios, we can say two cases. Either the projectile is going to drop after the target or it's going to drop before the target. Looking at the diagram, we can also say one thing, that since the angle theta is an average of alpha and beta, the projectile range is going to be somewhere between the range that was defined by alpha and beta. So if theta lies ahead of the target, then we are going to get a new maximum range. And likewise, if the projectile drops before the target, then we are going to set a new minimum range for the search space. This way, we are finally, in a very less number of iterations, log n, so to say, we are going to converge over an optimal value of theta that is going to finally hit the other tank. Now you might have observed in the advanced case, the opponent tank was not able to hit the targets for the first few times, but after it started to hit the target a few times, it was actually hitting at the right place. This was because after a few number of iterations, the search space was reduced to such a small value that an average was approximately the lower value, the average and the maximum value were approximately equal. That's why the converged value was not changing at all finally. Now, after we have calculated or converged to an optimal value of theta, we can likewise, as we have did in a simple case, calculate the horizontal and the vertical velocity and assign it to the projectile that we are going to send. Alright, so this was all for the explanation that we had to do for the complete AI algorithm. Now let's see how we have implemented all of this AI in the code. So let's get to it. So here we are in the code. For the simple case, we are actually using a function by the name of calculated aim. The purpose of this function is to return the velocity commands, so the tank can actually place the velocity commands on the projectile and make a shot out of it. Now this function takes two arguments, which are the target and the character. The character is the position of the tank itself and target is the position of the other tank. So here we are initializing the gravity and the steering. The gravity is being initialized by 0 and 9.8. Now this is positive because the coordinates of the window, the game window that you saw, were actually opposite. The negative is in the upward direction and positive is in the downward direction. Then we calculate the distance of the target position and the character position, which is just the range of the projectile. Then we calculate the angle using arc sine function of C++ that provides us. Now here is a little subtle thing that we have done. We have actually calculated an angle which is pi minus the angle. Now why we have done this? This is because due to the symmetric nature of the simple parabola trajectory that we have, two complementary angles, if we can say alpha and alpha plus beta is equal to 90, both of them will have the same range when we throw them with the same initial speed. So we are just simply exploiting this property to actually get a trajectory that is way more bigger than a trajectory that is way more lower. Then we are calculating the final velocities. Now, as we discussed before, we actually have the max speed already set up, which is a constant that we set to the value of 100. Then we are finally returning that steering, which is the horizontal and the vertical initial velocities. For the other advanced case in which we also need to consider the drag, we actually have a complete class of that target intelligence. Let's see what that contains. Target intelligence contains some variables that store the values, or we can say it is the memory of the intelligence. We have the maximum angle, which we have set to pi by 4, the minimum angle that we have set to 0, the current angle that we are throwing at, the maximum and minimum angle range, and the current range that we have. We also have trials variable, which the use for which we will see later on. And we have two main functions, which are calculated aim, which actually returns the steering commands or the initial velocities, and refined targeting, which actually does the learning part, we can say. Now, how this first calculated aim works. Now, trial stores how many times the iterations have run, like how many turns the enemy has taken. If we are at the start and it is the first turn of the opponent, then we can simply put angle is equal to max angle, which we had set as pi by 4. For the second turn, we can assume the angle to be the minimum angle. And for the rest of the trials or iterations, we are going to set the angle as max angle plus minimum angle by 2. Now, why we are showing the projectile at maximum and minimum angle is to record the ranges of the projectile at the maximum angle and the minimum angle. And we calculate the linear speed, the ux and the uy using the max speed and cosine and sine. Now this if-else statement is to determine simply if the character is at the left or at the right of the other character. We make subtle changes according to them, and then we finally return the steering or the initial velocities. We also increment trial with it. Now let's come to the actual learning part. Now it's not technically called learning, it's actually a computational way to make learning happen. How this function works, takes two parameters, which are target and range. Target is the distance at which the projectile should have hit, and range is the actual place where that projectile actually hit. As discussed before, the first two turns are to determine the maximum angle range and the minimum angle range. Then we are doing the binary search type of setting. If the range is less than the target, then we are setting the maximum angle range to be the new range. Otherwise, we are setting the minimum angle range to be the same range. And then we adjust the maximum and minimum angles accordingly as well. Now, to understand this, we can think of it something like this. Enemy tank is at this position. The maximum angle projectile has hit over here, and the minimum one has hit over here. Now, if the new projectile comes and hits somewhere over here, we are going to adjust the maximum angle to this new value. Otherwise, if the new projectile comes and hits over here, then we are going to adjust the minimum value. And this is actually what we are doing in this code. Running a few iterations of this code will actually result in the enemy learning the position of the character tank, or the player tank, as to say. All right, so this was the complete code of how the AI of the enemy tank was working. And we are pretty much done for the complete video. So if you like the video, please press the like button and subscribe to the channel for more such videos. And thank you for watching. Bye.